Hi everyone, myself Ratna Kumar. I am working as an assistant professor in Saint Martin's Engineering College in the Department of Electrical and Electronics Engineering. Today, now I am going to discuss about speed control methods of three-phase induction motor. Speed control methods of three-phase induction motor. The three-phase induction motor is one of the frequently used electric motor in industrial applications due to its simplicity, reliability, and high efficiency. Such motors are used where constant torque and constant speed and high torques are required. Some of the applications of three-phase induction motors are pumps, conveyors, compressors, and machine tools. These are the some of the applications of three-phase induction motors. Three-phase induction motor is also called as constant speed motor because the speed of the slip of the induction motor is very small, approximately less than 3%. Based on this, we can say the three-phase induction motor is a constant speed motor. It is essentially used for constant speed drive systems. But many industries require variable speed applications. Traditionally, DC motors have been used in variable speed applications. But DC motors are very expensive. They require maintenance of commutators and brushes. Compared to DC motors, induction motors are very cheap, rugged in construction, and they require less maintenance because of there is no commutators. These motors are used in high power applications. Now, I am going to discuss about speed control methods of three-phase induction motor. We can control the speed of the induction motor in several methods. Every method has their own merits and demerits. The proper understanding of every method is very important for operation of the motor in industry that increase the productivity and reduce the operational cost. We can control the speed of the induction motor from stator side as well as rotor side. In from stator side, we can control the speed of the induction motor in four ways. One is by changing stator voltage control. Next one by changing the applied voltage. Next by changing the stator poles. Next by changing the frequency. These are the methods to control the speed of the induction motor from stator side. From rotor side, we can control the speed of the induction motor in three ways. One is by changing the rotor circuit resistance. Next one is by cascade connection. Third one is by injecting voltage into the rotor circuit. These are the methods to control the speed of the induction motor from rotor side. Okay. Now I am going to discuss about first method, that is speed control by changing the stator voltage. The torque developed by three-phase induction motor is directly proportional to square of the applied voltage. That is, torque is directly proportional to V square. To apply the variable voltage to the induction motor, we have to connect one three-phase auto transformer in between the supply and induction motor. Now I am drawing block diagram of stator voltage control method. All of you see here, I am drawing block diagram of three-phase induction motor with stator voltage control. This is the three-phase auto transformer. Three-phase auto transformer is connected in star connection. This is the three-phase supply. Three-phase auto transformer is connected to the induction motor. And induction motor is connected to the fan load or fan load. Here we are connected one three-phase auto transformer in between the supply and induction motor. Why we are connected three-phase auto transformer in between supply and induction motor? To apply the variable voltage to the induction motor. When we are wearing the three-phase auto transformer, we can apply variable voltage to the induction motor. Induction motor drives the fan load. If you observe the graph between torque versus speed, if you draw the graph between torque versus speed, you will get like this. This is at V volts. This one is at 0.9 volts. This is the torque developed by load. Torque developed by load. When I am applying V volts by wearing the three-phase auto transformer, the speed of the induction motor is assume N1. This is Ns, this is N1. When I am applying the V volts by wearing the three-phase auto transformer to the induction motor, the speed of the induction motor is N1. When I am decreasing the voltage from V volts to 0.9 volts, the speed of the induction motor is also decreases from N1 to N2. In this way, we can control the speed of the induction motor. If we increase the voltage, the speed of the induction motor will be increased. If we decrease the voltage, the speed of the induction motor will be decreased. But the limitation of this method is torque is directly proportional to square of the applied voltage. The torque developed by induction motor is square of the applied voltage. The larger change in voltage will give the larger small change in voltage. Small change in speed, sorry. The larger change in voltage will give the smaller change in speed. The larger change in voltage will increase the magnetic flux density. So this effect on the magnetic conditions of the motor and the overall performance of the motor. So that's why this method is rarely used, and it is very easiest method and cheap and very easiest method. Now I am going to discuss about second method, that is pole changing method. Second method is speed control by changing stator poles. Speed control of three-phase induction motor by changing stator poles. If you draw the graph between torque versus slip, you will get curve like this. This point is starting torque. This point is maximum torque. At this point, rotor speed is 0 and slip equals to 1. At this point, rotor speed is equals to synchronous speed and slip equals to 0 minimum. This point is called as SMT. SMT means slip at maximum torque. Generally, the torque equation of three-phase induction motor is K V square S R2 by R2 square plus S square X square. This is the general formula to calculate torque of the torque of three-phase induction motor. But here we have to maintain what is the condition? Full load torque should be constant. Full load torque should be constant. At full load torque, the slip of the induction motor is very less. At full load torque, the slip of the induction motor, full load condition, the slip of the induction motor is very small. When slip of the induction motor is very small, the s square x2 square term will be very small compared to r2 square term. So we can neglect the term s square x2 square because it is very small compared to rotor resistance r2 square term. Now we can write the above equation. The modified full load torque is kv square s r2 by r2 square. Here r2 and square cancel. Remaining equation kv square s by r2. This is the full load torque, where k is the constant, v is the supply voltage, s is the slip, and r2 is the rotor resistance. Here I am not talking about voltage because we are discussing about pole changing method. So I am not talking about v square. Even I am not talking about R2 also, rotor resistance also. We are discussing about only pole changing method. Here K and slip. K is constant. We can write K equals to 3 by omega s. Omega s equals to 2 pi ns. Ns is called as synchronous speed. We can write ns equals to 120 f by p. Ns equals to 120 f by p. So we can write directly k is directly proportional to number of poles. K is directly proportional to number of poles. Now substitute k equals to p in this equation. Full load torque equals to P V square S by R2. I am not talking about starter voltage and rotor resistance. Okay, here poles and slip equals to constant. Why? Here we are taking condition full load torque should be constant. That's why poles into slip equals to constant. From this equation, we can write slip is directly proportional to 1 by P, 1 by poles. That means slip is inversely proportional to poles. If number of poles increases, slip will be decreased. If slip decreases, what about the speed of the induction motor? What about the speed of the induction motor? If slip decreases, the speed of induction motor will be increased. If number of poles decreases, slip will be increased. When slip increases, speed of the induction motor will be reduced. So in this way, we can control the speed of the induction motor by pole changing method. You may have doubt here. Speed control of three-phase induction motor by pole changing method is applicable to squirrel cage induction motor. Why? This method is difficult to apply slip ring induction motor. Now we are going to discuss about why it is difficult to apply slip ring induction motor and why it is easy to apply slip ring and squirrel cage induction motor. This is a slip ring induction motor. Here squirrel cage induction motor. Based on rotor construction, induction motors are classified into two types. One is the squirrel cage induction motor. Second one is slip ring induction motor. Okay, slip ring induction motor has a rotor, stator, and a rotor. Rotor is have a distributed winding with 6 poles. Assume now here stator is designed with a 6 poles. Rotor also, this one is rotor. Rotor also having distributed winding. Rotor also having distributed winding with 6 pole. At 6 pole, rotor is rotating at, assume here 1000 rpm. At 6 pole, the speed of the rotor is 1000 rpm. Now I want to change the speed of the motor. Again, I have to change the stator poles from 6 to 4. Here assume I changed stator poles from 6 to 4 pole. Not enough that, we have to change the rotor poles also. This is the main drawback for slip ring induction motor. It is difficult to change the number of poles, stator as well as rotor, for every speed. So that's why pole changing method is difficult to apply for slip ring induction motor. Coming to the squirrel cage induction motor, here when in slip ring induction motor, when stator poles equals to here rotor pole, stator poles should be equal to rotor poles. If stator poles not equal to rotor poles, the speed of the motor will be 0. Motor doesn't move. So that's why here we have to design equal number of stator and rotor poles. Coming to the squirrel cage induction motor, in squirrel cage induction motor, it is having stator as well as rotor. In squirrel cage induction motor, we have stator, rotor is a skewed rotor copper bars. We are using here not winding, skewed rotor copper bars. Here stator also designed with a, it is having distributed winding. Assume here 6 poles. The same number here in squirrel cage induction motor, no need to design rotor winding with 6 poles. Here automatically the same number of poles will be projected on the rotor. This is the main advantage of squirrel cage induction motor. Due to magnetic replica, the same number of stator poles, that is 6 or 4 or 8, whatever it is, the same number of stator poles will be projected on rotor. This is the main advantage of squirrel cage induction motor. That's why pole changing method is very easy to apply squirrel cage induction motor. Next, another method. Next, another method, variable frequency method. Third method is variable frequency method. In this method, we can control the speed of the induction motor by varying the frequency. We know the relation between slip synchronous speed and rotor speed. Here Nr equals to 1 minus S into Ns. Nr equals to 1 minus S into Ns. Nr is directly proportional to Ns. But we know Ns equals to 120 F by P. Ns equals to 120 F by P. By varying the frequency and the number of poles, we can change the speed of the induction motor. The induced EMF in a three-phase induction motor is E equals to 4.44 F 5 T kW. This is the equation to calculate induced EMF in a induction motor. E equals to 4.44 F 5 T kW, where F indicates frequency, phi is the flux, T is the number of turns, and kW is the winding factor. But E is directly proportional to induced EMF in a rotor is directly proportional to supply voltage. So we can substitute E equals to V here. In place of E, we can substitute V. V equals to 4.44 F 5 T kW. From this equation, we can write V by F equals to 4.44 T kW into 5. You can write directly V by F is directly proportional to flux. V by F is directly proportional to flux. If increase the frequency, flux will be decreased. If you decrease the frequency, flux will be increased. Okay, if you draw the graph between frequency, voltage versus frequency, you will get curve like this. This is the voltage, this one is frequency. This, if you draw the graph between frequency versus voltage, you will get graph like this. Here, this point is called as base frequency. This point is called as base frequency. Up to base frequency, we can vary the both voltage and frequency. Up to a base frequency, we can vary the both voltage and frequency. This method is called as V by F control method. V by F control method is used to up to base frequency only. If you increase the frequency above the base value, we go for variable frequency method. Here, in this duration, V is constant. In this way, we can control the speed of the induction motor by changing frequency. Here, we can observe the speed control in two cases. On case 1, when frequency increases, flux will be increased. When flux, if as the frequency increases, flux will be increased. When flux increases, the motor moves into the saturation mode. In saturation mode, very high currents will flow through the circuit. Second condition, when frequency increases, flux will be decreased. When frequency increases, flux will be decreased. In this condition, the torque developed by the induction motor will be reduced. So finally, in this condition, when torque is decreasing, the motor does not move. So in this way, we can control the speed of the induction motor. Now, I am going to give a small video on speed control of three-phase induction motor. All of you see a small video on speed control methods of three-phase induction motor. See here. All of this is small video on speed control methods of three-phase induction motor. Here, synchronous speed. What is the synchronous speed? Synchronous speed is the speed difference between the rotating magnetic field of the stator and the mechanical speed of the rotor. Here, the synchronous speed, we can calculate the synchronous speed by using equation ns equals to 120 F by P, where F is frequency, P is the number of poles. But yeah, NR equals to, NR means rotor speed. NR equals to 1 minus S into NS, where NS is called as synchronous speed. The speed control of three-phase induction motor can be done through various methods. Each method has own advantages and disadvantages. We can control the speed of the induction motor from stator side as well as rotor side. From stator side, we can control the speed of the induction motor in four ways. One is the frequency control method or V by F control method. Second one is stator voltage control method. Third one is pole changing method. Frequency control method. In this method, we can control the speed of the induction motor by varying the frequency. Already we have seen a small derivation on how we are varying the frequency, how to control the speed of the induction motor. The induced EMF in a rotor conductor is E equals to 4.44 F5 T kW. From the E is directly proportional to supply voltage. From that equation, we can write V by F equals to 4.44 F 4.44 T kW into F. So V by F is directly proportional to flux. By varying the supply voltage and frequency, we can control the speed of the induction motor. When frequency decreases, flux will be increased. When flux increases, in this condition, the motor moves in saturation mode. In saturation mode, very high currents will flow through the circuits. When frequency increases, flux will be decreased. In this motor, the torque developed by the induction motor is reduces, and finally, the motor doesn't move in this condition. Next method is stator voltage control method. In this method, we can control the speed of the induction motor by varying the stator voltage. To vary the stator voltage, we have to connect the three-phase auto transformer in between the supply and induction motor. By varying the stator voltage, we can apply the variable voltage to the induction motor based on our requirement. Next one is you can control the speed of the induction motor. Next, third method is from rotor side we have two methods. One is the rotor resistance control method. Second one is cascade method. The third one is by injecting injecting EMF into the rotor circuit. Coming to the rotor resistance control method, when we are varying the rotor resistance, we can control the speed of the induction motor. But the main drawback of this method is copper losses are very high. Due to copper losses, overall efficiency of the machine will be decreases, and temperature also increases. So that's why this method is rarely used. Next method is EMF injected into the rotor circuit. When injected EMF is in phase with the rotor induced EMF, we will get the speed of the when injected EMF is in phase with the rotor induced EMF, the resistance of the motor will be decreases. So when resistance is decreases, automatically slip will be changed. When resistance will be decreases, slip will be changed. In this way, we can control the speed of the induction motor. Thank you.